All right, everyone. Welcome back to the Synthesis Workshop podcast. Today, I'm joined by Professor Loi Do, who is an associate professor here at University of Houston. I got my biases in here. I can host Houston faculty as much on here as I'd like. So, but we have some stellar research going on here at Houston. So, if you're a viewer, you have to deal with it because I think it's really cool, and I'm the host of this podcast, so I can do what I want. But nonetheless, today, like I mentioned, I'm joined by Professor Loi Do, and his research group does a lot, well, kind of broadly, I guess, organometallics, but kind of wide variety of intracellular chemistry, but also polymerization. So kind of widespread, and we certainly will discuss that in good time. But like always, we'll start with your background because it's quite an interesting background. So you grew up in California, but did your undergraduate at UCSD, but also I noticed too that you also did some visiting at MIT, I think. So I'd love to hear kind of your background in that, but also, yeah, how you got the opportunity to do work some at MIT.
Sure, yeah. Well, thank you for having me, Aiden. Yeah, so like Aiden said, I did my undergrad at UC San Diego, and I started undergraduate research pretty early on in my sophomore year with Seth Cohen. And this was back when he was an assistant professor, so it was great. I had a lot of attention. And so this is like the early days of moth chemistry. So I got to make, the diperin ligands, made metal complexes. And then I really enjoyed research. I'm a very hands-on person, so that was sort of a good match with kind of my interests and what I wanted to do in the future. And so Seth did a postdoc with Steve Lippard at MIT. And so one summer when I was trying to think of, RU programs to apply to, he was like, hey, why don't you go work for Lippard for a summer and see what happens? And so that was how I got the spend some time there in Boston for a summer. And there I was working on conjugated polymers for NO sensing. So it was a totally different project, but it was still really fun. And I got to make fluorescent materials. And so I really got into spectroscopy. And so I was there for that summer and then went back. And that was my senior year. And so that experience sort of solidified my kind of, basically confirmed that I wanted to go to grad school and kind of develop further in research.
Yeah, I probably should have started with this, but I definitely I didn't enter in that well. But let's take it even a further step back then, because I forgot to mention this, but yeah, you grew up in Southern California. Well, did you grow up in Southern California, or?
So no, actually, I was born in Vietnam.
Oh, okay, yeah.
My
Okay.
family and I moved to the U.S. To San Jose, so NorCal, when I was 6 years old. And then, I was in San Diego for 4 years. And then I did my postdoc in, Caltech. So I've sort of been up and down California.
Yeah. Now, do you? I mean, 6 years old. Probably don't remember anything about Vietnam, or have you visited there since? Or
Yeah, I have actually. I went back for the first time in 2018,
oh wow,
and so that was a long time since I left. Of course, when you're 6 years old, you don't really have much memory of your childhood. But I did have sort of vague memories of like the neighborhood and like our house. And so it was kind of neat to go back and we lived in Saigon, and it's very modern now, but it wasn't modern when I was there. So it's really interesting.
yeah. I had to pull up a map of Vietnam because I need to kind of get my bearings here. I know Hanoi is on like the northern end, but
Right.
I'm not really sure. Do you, well, you said your parents moved here, right? So I don't know. I assume you have family back over in Vietnam. So I presume
Yeah.
you're visiting some family, or?
So yeah, I was actually I was visiting some family, but it was actually part of my trip. I had a conference in Singapore.
Oh wow, okay,
I
yeah,
think I did like a kind of a side trip to visit.
yeah. That's really that's really cool. I definitely I've yet to be anywhere to any of the Asian countries yet, but it's definitely a destination for myself to get over there and visit. Um, any while you were there, any cool spots that perhaps people should go and check out over there? I
Yeah,
don't
no,
know.
I think it's a really fun place to visit. There's lots of great food.
Mm.
Um, I unfortunately don't really speak Vietnamese, so I had luckily a tour guide with me when I visited that time. Um, yeah, I think it's just a very laid back trip.
Yeah.
It's a lot of eating, a lot of sightseeing, and
Hmm.
we bike through the countryside. That was really
Right.
nice.
Yeah. That's pretty groovy. So yeah. So grew up in. I guess you said, like you said, you grew up in San Jose, but then did your undergrad at UCSD.
Right.
How did let's go there a little bit. Why? What kind of attracted you to go to UCSD? And even maybe even before that too. Like, what kind of did you enter in as a chemistry major, or what? Like, what was kind of like your
Sure. Yeah.
kind of how'd you enter into that whole?
Great question. Yeah, so when I was deciding on colleges, my parents wanted me to go to UC Berkeley because it's 45 minutes away from San Jose.
Hmm.
But I kind of wanted to move a little further just to kind of expand my horizons a little bit. And then fortunately, I got a scholarship at UCSD, and so my parents, it was relatively easy to convince them that it's financially sound to move away. And so that's how I made that decision. Um, I didn't go into college with the intention of majoring in chemistry, actually. So in high school, I didn't take AP chemistry or anything, just regular chemistry, and it
Oh
didn't
wow.
really stick out to me. It wasn't really one of my favorite subjects until I took freshman chem, so Gen Chem. And that's when I really learned the periodic table, and it was just like, wow, this is like nothing I had learned in high school. And then I discovered that I really love being in the lab. While a lot of my classmates hated lab work, I was the opposite. I just love making things, and I think that's what really drew me in.
Hmm. It definitely is something about the hands-on work. I think that, except for maybe computational chemists, but hands-on work. That's kind of the connecting tissue. I think probably between all
Right.
chemists. Honestly, it's like the hands-on. Nowadays it's you can you could have like surround sound with your speakers and stuff like that, but it's something about like just kind of putting in your headphones and doing some lab work is this a little bit of serenity to it. Um,
Sure. Yeah. Yeah.
Oftentimes. So.
I think that's definitely true for most synthetic chemists. For me, I remember when I was an undergrad, it made it real. You know what I mean? Like, so,
Mm,
like, I was learning organic chemistry in class, and I was literally going to my research lab and using those same reactions to make my molecules.
mm,
And I always tell my undergrads this is that, like, once you've had that connection, it's no longer just a theoretical
yes.
framework, right? Like this is something that is practical and useful, and so I try to convey that when I teach that
Mm,
this is not just random facts. Like you could actually use this knowledge.
right. We're trying to convert as many MD doctors or on the track to
Right.
chemistry. That's always the
Exactly.
goal, right?
Yeah. Well, now I'm teaching the honors organic section, and that's like 90% pre-med.
Right.
So,
Right. They're all pre med or they're all like going to like PT
right.
school or something
Right.
like that, and we're gonna try
Right.
and convert them over, see what they're missing out. But yeah, that's such a great point, and probably like is probably advice for professors teaching is really trying to make that connection between writing on the board and actually in lab. I think that's extremely important
Right.
point for
I think
18 to 20-year-olds.
from the teaching perspective is really hard to convey that excitement to students in a lecture hall,
Mm.
because you're drawing reactions on the board, and to the student they're just arrows and figures.
Triangles and hexagons. It doesn't really
Yeah,
mean anything.
exactly. Right. So for organic chemistry, I've always wanted to kind of couple that with like doing class demos, but it's just not possible with the way that our lecture halls are structured, right? There are no chemical fume hoods, for example.
Mm.
And so actually in my biochemistry course, which I teach in the spring semester, I do little demos in class. And that way, at least the intention is to kind of show, hey, the knowledge that we're discussing here can be applied into a real situation.
Yeah.
Um, I think that works the best.
Yeah. I that's so cool you do that. And I actually I kind of I'm a bit envious because when I took biochemistry, it was my senior year of undergrad, but that was during COVID. So it was like I kind of always say it's like I took inorganic chemistry, physical chemistry, and biochemistry all during COVID. suffice to say, I didn't really learn much. No, that's not on the professors. It's just like
Right.
a 21-year-old is like, I'm just not gonna
Right.
take it too seriously, you know?
Yeah,
Um,
that's really unfortunate. So back at UC San Diego when I was in college, we biochemistry is part of chemistry, and there's like a like a sub focus. So I was a chemistry slash biochemistry major,
mhm.
and so part of that, I took several biochemistry labs, and I think that was a really great experience because it gave a nice complement to the synthetic labs that most chemistry majors took. And basically, what it taught me is that, well, chemistry is beyond just their typical let's make molecules, right? But chemistry is essential to life processes and
Right.
biomolecules and so on.
It's like chemistry and physics are the central sciences, and biology is not. I always hear that from people. Not that I agree with it. I always thought it was a good joke, like just to poke
It's
some
just
fun at it.
different ways of looking at kind of the physical world, right?
Right.
Biology is like top down, whereas chemistry is like the bottom up. So
Yeah.
different lens.
It is very unique, and biochemistry tends to be a good mesh. So it is.
Yeah,
I definitely
absolutely.
agree, and hopefully, we start teaching, or hopefully, the way that we teach chemistry can kind of adapt a little bit in that sense, and kind of making it a little bit more hands on if you're able to, as much as you
Right,
can anyway. So, but
right.
so like you mentioned, though, you had done undergraduate research with Professor Stephen Lippard. Just a little bit again. How did the opportunity arise? Like, I mean, were you taking his class? Like, how did that kind of come about then to do undergraduate
Uh,
research?
with Seth Cohen back at
Oh,
UCSD.
yeah, Seth Cohen. Yeah, I'm sorry. Yeah,
Okay, yeah.
Lippard was
So that was
MIT. That's right.
actually, I guess there was a like a student faculty mentor program, and faculty can request undergraduate students to work with in the summer. And so I was lucky that I got paired up with Seth because I didn't actually know him prior to joining his lab, and so it was just fortunate that I was there at the right time. I think working with him as an assistant professor was really valuable, because like I said, he spent a lot of one-on-one time with me. In fact, I remember very vividly one of the first experiments I did was coming out on a Saturday and running a column. And he taught me how to run a column,
That's
and
so cool.
I was so amazed, right? Like, wow, what is this? Like colors, like, So like that was really neat. And then just feeling part like an important part of the research program made me really wanted to put in time in the lab.
Mm,
Because I think, especially if you work for like an established professor, it's hard to have a lot of one-on-one time.
right.
But so I had sort of a unique experience because of
Yeah.
that.
I often say this a lot. Like, if you're an undergrad or a graduate student looking to join a lab, there is a certain uniqueness to joining an assistant professor, because you often, more often than not, you will get those one-on-one time with them. They he or she are trying to build their lab, so they need to get the work out, and so they need students to do this work, and so they'll often, that first batch, they got to teach them, right? So they got to teach them a lot of the ropes, right? um so it's definitely a unique experience, and if it lines up for an undergrad or a graduate to do that, I would highly consider it, because it's definitely a unique experience, kind of setting up a lab or being with an assistant professor.
Yeah, I
um
definitely agree with that. Especially if you're thinking about starting your own research program in the future, or
mm,
building a lab. I think you learn a lot of important skills.
right. That just, yeah, especially, yeah, beyond the chemistry, right? I mean, I don't even, I don't know. Maybe we can talk about this a bit later on, but starting up a lab, like, what do you even, that actually would be a good episode. Like, what does it even take to start a lab?
Yeah,
You know what I mean? Like, what is, maybe I'll probably actually ask that later on. I'll come back to the, because I
sure.
don't know.
Yeah, yeah.
That'd
A
be
lots of
really
thoughts on
interesting.
that one.
Um, but, you're doing undergraduate research, I guess. Uh, Beyond that, going to graduate school, was that MIT, right?
It was also MIT, right?
MIT.
Yeah, yeah.
So then, was it kind of a natural progression then to go to graduate school? Like, how did that kind of opportunity go?
Yeah, it's a great question. Undergrad and grad school is so different, right? Um, I think I was lucky that I sort of got an experience at MIT, the summer prior to going grad school. So I kind of knew what being a graduate student was like, what the lifestyle is like. But I think there's still a lot of just learning as you go, because I was used to having a lot of attention in the lab. And when I started as a first year graduate student, Lippard's lab was very different, right? I think they had maybe 25 to 30 people in the lab, very large group. Lippard at the time was a department chair, right? And so he didn't have a lot of one-on-one time with students.
Right.
And so I think as a first year graduate student, I had to learn how to navigate kind of within those confines. Is that, okay, well, I don't really know much about my project. I'm still learning. And so, I had to figure out, well, how do I get into the research, get the help I need, and so on.
Yeah. Yeah. It's definitely there's some, because I like most people, I guess, who are in grad school, most people will have done undergraduate research, but there definitely is, even though you have some background, there still is a jump to graduate school that you really can't really prepare for, right? You're just gonna hop in,
Exactly.
and of course, you're gonna have some, most of the time you'll have senior students or that professors as an advisor, but you're kind of somewhat on your own. Like you kind of have to learn. You have to learn so much, like on your own. Like you really kind of on your own in a sense. And so, yeah, I definitely hear that. Now, what was the attraction to join his lab? Was it Lippard's?
Yeah, so I really got into just inorganic chemistry in general because I work with Seth Cohen, and I was really just fell in love with making these metal complexes. It's just, pretty colors, and it does all sorts of interesting things. So I knew I wanted to do inorganic chemistry, so I was there as an inorganic chemistry student, which is ironic because now I'm teaching organic chemistry.
It all starts to blend together, honestly.
Right. And so I like Lippard's lab because his research is very diverse. And so that's kind of the way I think. I just, I don't confine myself to within a certain subdiscipline. I kind of think more in terms of the research problem and kind of finding the tools to address those issues. I was also interested in Tim Swager's lab. So they work on like conjugated polymers for sensing applications. So those are the top two labs that I was considering in graduate school.
Mm-hmm. Yeah, so I know you're working on kind of like protein modeling, right? I think.
Yeah, so we were looking at trying to model the active sites of diiron-containing proteins. Specifically, we're looking at this enzyme called methane monooxygenase, which takes methane to methanol, which from a chemistry standpoint is really amazing because this is happening under physiological conditions, right? So pressure and temperature is very selective, right? Because if you try to oxidize methane in the lab, you likely get carboxylates or something, right? Or CO2.
Whole bunch of stuff, probably.
Right, exactly. So nature does chemistry that we can't really replicate, right? And as far as we advance in chemistry, that still really amazes me that the secrets that it's within these enzymes really hasn't, we haven't really quite understood how it works.
Right. I can already see the imprints into your lab now. You see that back as a graduate student, you're kind of that impression of like the biocatalysis now.
Right.
It's kind of coming full circle in some sense.
Yep.
Yeah, that is interesting. Maybe we could touch on that a little bit, perhaps for some viewers, like, what it actually takes to oxidize methane to methanol. Like, what does that actually mean? And also perhaps the societal implications of that. Like what, like,
Sure,
I don't know.
Well, I guess in terms of the societal implications, methane is a potent greenhouse gas, whereas methanol is very useful, for example, solvents in the lab or just, a way to transport also, right? To transport materials because it's a liquid at room temperature. So biology could do this really well because it uses molecular oxygen. So it transfers one oxygen from O2 to methane to produce methanol. And so synthetically, we don't really have the tools to do that, to take molecular oxygen at room temperature, ambient, pressures, and selectively oxidize methane, or even just hydrocarbons in general. Like it's very difficult to do it with O2 as your starting oxidant.
Yeah. Is it well understood how the body does it? So this protein, is it kind of really well understood how the protein's able to oxidize methane, or is it?
Yeah, so the hypothesis is that there are actually two different types of enzymes that can do it. Either a diiron-containing enzyme or a copper-containing
Mm,
membrane-bound enzyme. The one I was studying was a diiron center, and so the idea is that it activates O2 and it makes an iron 4 mu-oxo intermediate, and
okay.
that is a highly oxidizing species, and so it can transfer the O2 from that intermediate.
Oh, that's really cool. Okay. So
And
if okay, okay, I got you. I follow that. That's really cool. That's really. Um, was that so? I guess was that a theme of Lippard's lab? Then it was kind of just proteins in general, or what was like?
yeah, so Lippard is kind of considered one of the big players in bioinorganic chemistry.
Mm,
And so his lab at the time when I was there was working on four very different areas. So I think the research that he's most well known for is work on cisplatin, the anti-cancer drug.
yeah.
So
Okay.
they were trying to understand basically how it works, right? What does it bind to? What are the mechanisms of activation and so on, and deactivation? He was also working on sensing. So he was developing sensors for like zinc. That was a big one. Sensors for nitric oxide. And so there's a lot of biological significance of those things. That's why they're working on it. And then in my subgroup, we're the synthetic subgroup in the lab because we didn't do any biology, at least in my subgroup.
Right.
And so we were purely using synthetic chemistry to try to understand biology, basically.
Hmm. So I guess in your 5 years, or was there any like big conclusions or anything you kind of really take away from what you had been studying, or
The big conclusion is that
we
trying
still
to
don't know
mimic
much?
trying to mimic nature is extremely hard.
Yeah, it's got a billion year head start. To be fair.
So I was happy that I was able to make a structural mimic of that protein active site, which took 5 years to do, but it was not
Nice.
functional, right? I like to say it's just like a trophy molecule, right? I can put it on my desk and say, "Hey, look, I made the structure." But it's hard because I wasn't using the same ligands that nature did, right?
Mm,
I had to make it a macro cycle, and then it had like phenols instead of carboxylates. It had an imine instead of an imidazole group. And so since synthetic chemistry, we have to sort of use tricks to try to mimic nature. But because we're using these tricks, it's not truly replicating the natural cofactor.
right.
And plus, we don't have the enzyme. Enzyme is critical because it can access geometries that are difficult to access with a small molecule,
Right.
right? So in
Yeah.
some ways, it's sort of like testing the limits of synthetic chemistry. Is how close can we get to nature without actually using nature's molecule, which is the
Mm,
enzyme.
yeah. Was there any reason you guys just weren't using the enzymes in particular, or I don't
Well,
like?
so part of it was to try to study the chemistry in a well-defined system.
Okay.
So the lab actually studies the enzyme, the native enzyme, and that's a separate subgroup from my subgroup. So we're basically taking two different approaches, trying to understand the chemistry using biochemical methods, studying the natural system. At the same time, we're trying to look at these synthetic mimics to try to gain more insight from a kind of a molecular atomic level.
Mm,
Because with proteins, because they are macromolecules, trying to get structures of intermediates is really difficult. For example, just trapping enough intermediates to study spectroscopically is sometimes extremely challenging. So that was kind of the motivation to have these synthetic complexes where we can replicate the active site and then maybe try to understand, at least characterize some of the intermediates in
yeah.
that pathway.
Yeah. Yeah. That's definitely the kind of the census I get from a lot of people who try to study, um, biological systems, but with I would say synthetic methods, is that it's just difficult. It is extremely difficult. Um, like nature has had millions of years to do these things to get it right, and we're trying to play catch up and really just understand these systems. And but I'm glad to see that this. I'm always glad to see that this work is always trying to be done, and so work like this is super fundamental.
Yeah,
Um,
definitely. I think you hit it right on the nails. It's the fundamental chemistry that we're after.
right.
But I think as a graduate student, it was really a great project because it taught me so much.
Mm.
right? Actually, I spent probably the first couple of years learning organic chemistry. And again, thinking, I was an inorganic student, so I wasn't
Yeah.
expecting to learn all of this synthesis. But in hindsight, like it was extremely valuable, right? Just learning how to troubleshoot because, a lot of the early ligands that I made never got published
Mm.
because it just didn't bind to iron the way we wanted to, right? And so, the early versions of the ligands really didn't give us very interesting results. But from a training standpoint, it was a really great training because I
Right.
learned kind of a broad range of chemistry. I learned, lots of purification techniques, and just kind of persistence, right? I think more importantly, it's just when things don't work, instead of banging your head against the wall, you gotta kind of troubleshoot and kind of think through your design.
Yeah. That's great to hear. So, following your graduate studies, you had um, gone on to do some postdoc with legendary, Professor John Bercaw. Honestly, I think he's a legend in the field. For those that are outside chemistry, that guy is a legend,
Yeah.
especially when you talk about polymers. Um, now, was it this point you'd really had begun to think about becoming a professor? Or had that really kind of entered your mind yet, or um, but also maybe before you answer that though, was a postdoc a natural progression? Like, was that kind of
Yeah,
a
that's a really interesting question. Actually, I've always was interested in academics or academic jobs, even back in college.
mm,
So actually, I was a undergrad TA for a recitation of organic chemistry in college, and that was my first real experience in teaching. And so I really love that. Like I just love being able to get on the board, explain something, you see that light bulb go off in their heads.
yep,
And that was a really rewarding experience. It's like, hey, I'm good at something, basically, right? That I could potentially do with my life. And then coupled with kind of the experience I was having in the lab, that I also love being in the lab doing research. Being an academic seemed kind of amalgamation of those two things I really enjoyed, right? Teaching and research.
right,
And so going into graduate school, I actually already had sort of that intention of pursuing that route. But I think during graduate school, I did go, there was sort of ups and downs, and I
sure.
sort of did consider, okay, what about industry jobs? I actually did apply to industry jobs after my postdoc, but ultimately, I'm here. But I think both routes um, are interesting routes to pursue. I don't think one is better than the other. It's just that's where it landed me.
Certainly feels like, well, the opinion I get is, getting a professorship is difficult. It's a very competitive market. That's the only thing I'll really say. But if you're really passionate about fundamental research, I mean, that's the pathway then.
Right.
I would say. But like I said, so you went back to Caltech. Oh, one other thing I wanted to ask though is, were you prepared at all for those Boston winters coming from California? I don't think anything could really prepare you for that.
No. So again, I went from San Diego to Boston, right? So San Diego is like sunny all year round, 70 degrees, beautiful. So I never saw snow prior to going to Boston. So
Yep.
that first winter, actually the very first couple of weeks was fun, right? It's like, oh, nice fluffy snow,
Yeah.
soft, pretty, until it starts getting, slushy, and then you gotta like wake up early in the morning to take the train. You gotta like um
It's
so that
brutal.
was interesting. Yeah,
Nope.
so that was a
It's
different
a, it's something I always like to ask people who kind of grew up in California, particularly like the southern, but also kind of maybe middle California, to move to, people that moved to like Rochester or Buffalo or,
right.
Boston. Like, those winters are real deal. Like, that's the
Yeah.
real deal.
But Boston is still not as bad as say Buffalo or
It's
like
not.
Midwest, right?
That's the
So
thing. Or like Minnesota, like University of Minnesota, man, or like Chicago. Oh
oh yeah,
man,
yep.
those are brutal. Um, Great research institutes, but I my hats off to those that get up at 7 a.m. trudging through the winters, because that's tough.
Yeah, because I'm an early morning person, right? So
Mm.
I got on like the first train, and it's completely dark, and when it's like ice on the on the sidewalks, yeah, those were hard times trying to get out the door.
and in the height of winter, in the East Coast, it's like dark by like 4:30. So you'll get up if you're, let's say you're a morning person,
Right.
at 6, 8 a.m. It's still dark out,
Right.
and then you're working all day. Maybe you get outside, but by 4:30 it's dark. So it's quite a, those. It's a. I will say, just if you're kind of a, I don't know if moody person is the right word, but if it the weather has an effect on your emotions. Let's put it that way. And if you're someone that likes the sun, just consider that, because in the wintertime you hardly get any up in the
Yeah,
Northeast.
I'm definitely one of those people who's very affected by the weather.
Yeah,
So
same.
if it's gloomy, I am just like really slow and sluggish, and when it's sunny, I'm like really bouncy.
Yeah,
But so yeah, that was the hard part. Is that in Boston, it was cold for a really long time. It felt like, and when spring finally came, it's like, oh, freedom.
yeah, right. And it's funny because it's the opposite here. It's like summer. I'm dreading the summer now because now it's going to be 100 degrees plus humidity,
Right. Yeah.
and people are like, "Oh, you must get great weather in Texas." It's like, I mean, in
Wait, so
Houston, out like, I'm sorry.
where did you grow up?
I actually grew up in Philadelphia,
Ah, okay. Yeah, so
suburbs. So
you're familiar with cold weather then.
yeah, familiar with cold weather, the seasons,
Hmm.
and dark by 4:30 on in the winters, and Houston is great, but man, those summers are hot. They get pretty hot down here. Um, anyway, what are we talking about? Oh yeah. So you go back to Caltech, join Professor. I guess there's a few questions I have here because Professor John Bercaw, huge in polymer science, but your background really isn't in
Right.
polymers at all. But also just the idea of doing a postdoc with John in general. So kind of how did that opportunity arise, and what
Yeah.
was the interest there?
So I got really interested in catalysis just because we were studying protein catalysis, right? And then so I wanted to kind of expand my knowledge of catalysis into kind of industrial chemistry. And so John Bercaw seemed like a perfect fit because he works on a lot of really fundamental organometallic chemistry that's relevant to industry. And so when I was with John, I was working on chromium ethylene trimerization. So you're starting from ethylene to make one hexene specifically. And so that program was supported by BP.
Mm.
And so that was a really neat experience because every year we would visit various sites. Like BP has sites all around the world, and we would get to see kind of their industrial sites. For example, we went to Seattle. We had one trip we went to the UK, which is like their headquarters. So it's kind of to see chemistry, applied in kind of very different contexts.
And what's BP again, or what's
It's the oil company,
okay?
BP. Yeah.
It's literally BP. There's no it's not a
Yeah, I
contraction.
think it's British Petroleum. I
Okay,
got to check on that one, but
it's okay.
yeah, I think that's what it stands for. Um, but so that was a cool experience. That gave, I think that's what you want in a postdoc, to kind of expand your expertise, your knowledge,
Hmm.
and so that's what I got. Um, and so I think you can kind of see it in my independent program that it is very broad, and that's influenced by my training.
Yeah,
You know.
yeah, and yeah. So I mean, it must have been really cool. Any ethylene trimerization. What was the? Well, listen. From what when I've talked to other professors who've done postdocs with John Bercaw,
Yeah.
it's a very fundamental stuff. So was there kind of a reason you were interested in this? Or?
Yeah, well, so so specifically for a postdoc with John, I was really lucky to work with him because he's sort of known in the field to be very rigorous, very deep thinker, but also just a really good person, and
Yeah.
so I thought he would be a great mentor, and it's absolutely true. Everything positive about John is true, right? Um, and specifically, ethylene trimerization industry is interested because this is a selective reaction. So the way that it works is it forms these metallocycles. So ethylene reductively couples. So then you have like two ethylene units, and then it inserts another ethylene to form this metallocycle, and then it reductively eliminates. And so that's how you make the one hexene. And so this mechanism is really unique because the traditional catalysts were typically like the shop catalysts that make kind of a broad distribution of oligomers. right? And so in addition to getting one hexene, you're also getting, C4, C8, C10, C12, and so on. And so that's very inefficient, right? If you're
Right.
trying to get high yields of alpha olefins, like one hexene or one octene, you want a catalyst that can do that really well. And so the chromium systems were really amazing because they can get one hexene selectively. And there's some systems that can get a mixture of one hexene and one octene through a similar mechanism. But so that's the industrial interest is how these systems work, how do they improve it, and trying to understand fundamentally why they're different than the traditional, let's say, nickel catalyst.
Yeah, that's must be so cool. Yeah, I've John Bercaw is definitely someone I definitely want to meet. Even though I don't really do part of my subgroup does polymers. I personally don't really do polymer science, but he's definitely someone I'd love to meet someday.
Right? Yeah. Unfortunately, he's now retired, but
yeah,
he occasionally goes to conferences, I think, but not
that's
not
much.
often.
That's
Yeah.
all right. But following your postdoc though, you transitioned to now you're here at University of Houston. So perhaps we can talk about your research areas now. So, like I mentioned earlier, kind of integrating biology and chemistry with this, biocatalysis, but also polymerization. So I kind of let you take the floor here and maybe tell us a little bit about both areas of research in your group and, what one could expect, joining Professor Loi Do's group.
Sure. Yeah. So, sort of the central theme in my lab is catalysis. And so, even though the two projects, intracellular catalysis, polymerization catalysis, are very different with very different end goals, I think fundamentally it uses the same tools, right? We love thinking about structure. We love thinking about design. Is how do you design functional molecules, right? And we're focusing on catalysis, how to design uh, catalysts that are specific, that are efficient, and to adapt it for different applications. So in the intracellular catalysis subgroup, we're ultimately interested in developing catalytic drugs, right? So essentially you would take a pill and it would be able to, because it's a catalyst, be able to amplify reactions. And so you wouldn't, in theory, need a very large, or at least a large dose because it would persist and then you would be able to have the therapeutic effect. So that's sort of the pie in the sky goal for that subgroup. But fundamentally, we have to learn about, well, how do we even make a catalyst that work in a biological system? Right. So for my background as an organometallic chemist, we're trained to rigorously exclude air and water from everything, right?
Right.
I'm sure you have that experience as well in your lab. But now in our research, we're doing the opposite. We're putting water in everything, right? And we're running reactions under air. And so fundamentally, how do you even design catalysts that work under those conditions, right? Because often, especially with first world transition metals like iron or cobalt, if you have weak ligands, it would just fall apart. You put it in water, it gets displaced.
Yep.
Right. And so in some ways we're limited because we have to work with metals that can form relatively inert metal ligand bonds.
Yep.
So, for the past 10 years, we've mainly focused on iridium. That's kind of our workhorse, these CP star organometallic iridium complexes. They work great in water because they have relatively inert bonds to their supporting ligands. And so for that subgroup, we focus mostly on reaction development for the cell, right? So we would screen reactions usually under biologically relevant conditions. If it works well, then we put it into cells. So we actually have a separate cell culture lab in the building across the street. And then there, we're now able to look at in a living system, right? Which also has different challenges that we don't normally think about as a synthetic chemist, right?
Okay.
For example, just uptake, because when you add your molecule to your petri dish, it doesn't mean the molecules will go into the cell, right? We have to understand how it gets into the cell, how much gets into the cell. We have to think about toxicity, right? Are we causing the cells to? Are there negative effects on the cell? So there are lots of fundamental questions that we have to answer before we could develop a working catalyst for this. So that's kind of, in a nutshell, what that subgroup's working on.
And over the past 8 years or so, has anything kind of been learned? Like what's kind of been
Yeah, so
some key?
we now have a pretty good system with these CP star iridium compounds that do work in a cellular environment. One of the biggest challenges is trying to work in the presence of strong nucleophiles.
Okay.
So inside a living system, you have a lot of sulfur-containing species. So
Mm.
you've got things like glutathione, you've got cysteines, and those sulfur ligands love binding to soft metals, right? So if you got an iridium and you got a sulfur ligand, it's going to form a really strong coordination bond.
Mm.
So right now, the challenge is, well, how do you deal with that? Because that's going to be present in the biological environment wherever you are. And so we have different strategies that we're working on. We have one paper that came out recently where we designed like a macrocyclic structure. Well, the idea is that your substrate, your desired substrate, is small so that it can diffuse into your active site, whereas the larger molecules like glutathione might be able to be is too large to actually fit through
Mm.
to bind. So we're exploring various strategies to try to get around that problem. But so this is a fundamental issue or challenge with anything that you want to put into a cell, right? Especially any catalyst you want to put in the cell,
Mm.
is how do you deal with that, right? How do you manage substrate versus things that would inhibit your catalyst?
Yeah, it's definitely as someone who does organometallics, but in glove boxes and shrink lines, this is definitely something I do not have to worry about. But I love to see this fundamental research, and is it kind of, I guess, like in hindsight, like to think about like maybe proteins with thiols, like was that something that you even really could see coming? Like you know what I mean? Like what could you predict all these like issues? I guess I don't know.
Yeah, some of it, yes, just from basic understanding of inorganic chemistry, right? If you in inorganic chemistry, you learn about affinities of different ligands, different metals, hard-soft theory, right?
Mm.
And so I think those fundamental concepts do apply inside a living system. With biology, because of the enzyme structure, often the active site is very well protected, right?
Mm.
And often
Yeah.
there are like substrate channels, and so it's very specific. But in a small molecule, you don't have that advantage because you're completely exposed to the external environment, which is your solvent and anything that's containing that solution. So that's the challenge of using a small molecule is how do you deal with that?
Hmm.
Because
Yeah.
your catalyst exists in a dormant state, when it's bound to the sulfur, then
Yeah.
that means you don't really have much catalytically active species in solution.
Mm. Well, yeah, this is definitely is this is quite a interesting area of research, and I definitely like look forward to what comes out over the next few years and how you're able to deal with this. Um, but what about your polymer side? How does that kind of progressed?
Yeah, so on a polymer side, you know, we're working on olefin polymerization and something that's your lab is familiar with. And so we often get the question, especially in grant reviews, is why are we still working on this, right? Because as you know, this is a field that has been around for many decades now,
Yeah.
since the 1950s, actually, right? And so we often get the question is, well, what is there to innovate, right? There are literally hundreds of olefin polymerization catalysts. This is something that industry does on, enormous scales is polymerization of olefins. And so that was a great question for us when we got into it because, we saw opportunities from the fundamental chemistry standpoint,
Mm.
specifically in the polar monomer problem. As one of the big issues we want to address is, we have these catalysts that are super fast. They work great to polymerize ethylene, polymerize propylene. But when you have the polar functionalities, early transition metals are very oxophilic. They bind to these polar groups and they don't work very well. And so now there are systems that based on nickel and palladium that do incorporate these polar functional monomers. However, they're not very efficient, right? And so um, that's one challenge that we're trying to overcome is figure out, well, how do we make catalysts that are efficient that would be able to incorporate these interesting monomers? Um, Another concept that we are trying to explore in my lab is the idea of switchability.
Mm.
So there's a general field of switchable catalysis with the ideas that, you can take a single catalyst, switch it to different states to give you different products because you can change the reactivity. And that's been used really nice demonstration of that in various applications. But for polymerization specifically, most of the systems that are reported in the literature switch between 2 to 3 states, right? And
Mm.
so that means you'll get two to three different polymers, right? If you reduce the catalyst, you get one polymer. You oxidize the catalyst, you get a different polymer. And so in the polymer world, that's useful because often you want to be able to customize your polymers for whatever applications you ultimately want to use it for. And so being able to customize polymers on demand is really valuable. And so when we kind of thought about that, switching on and off, is still somewhat limiting because you're only limiting yourself to 2 different polymers.
Mm.
And so we thought maybe we can expand on that by using cations as switches. Because with
Okay.
cations, metal cations specifically, if you look at the periodic table, there are many different elements. They have different oxidation states. And so the idea is that we have a central platform where we can mix and match different metals, and that would switch the reactivity that provides us a way to exquisitely tune the polymer products that ultimately you obtain.
Okay. I'm trying. Yeah, I'm trying to follow this a little bit here because I'm not as familiar with the polymer world. So, is it this? Oh, I'm sorry. So it's the same catalyst,
Right.
or okay?
So
Then
that's the innovation, right? Because traditionally, if you want to make a certain type of polymer, you would have to select the catalyst that gives that type of polymer.
gotcha. Okay.
And so, in theory, if you have 1,000 different catalysts, then you could make 1,000 different polymers, which works, right? I mean, industry does this.
Sure.
But we wanted to kind of simplify it and to make a tunable catalyst,
Okay.
where you could have just one catalyst that can give you potentially an infinite number of polymers, right?
Mm.
Because you can dial it to however you want, right? And so that was kind of the concept when we first started.
Okay. I gotcha.
And we're getting pretty close to that. We definitely can't make infinite number of polymers, but there is a wide range that we can access now. And
Okay.
so in our latest paper that we published a couple years ago, we introduced the idea of dynamic switching using cations.
Yeah.
So the idea is that you have, let's say, a nickel catalyst, you pair that with a second metal, because we could use cation exchange equilibrium to control when it binds and when it comes off. We could basically use that to tune how the polymer grows. So maybe a way to explain this is, so let's say you have your nickel catalyst, you add in your
Mhm.
ethylene, so it would grow your polymer chain.
Gotcha.
And then because you have your cation in there, at some point the cation is going to bind, and when it's bound to your nickel, the polymer is going to continue growing, but let's say at a different rate, because now you have that, let's say, nickel lithium complex. Under the right conditions, that binding is reversible. And
Mm.
so the lithium could come on and off. And so as it comes on and off, it's going to change the way the polymer is growing. And so that ultimately affects the product, your polymer product at the end of it.
Gotcha. Okay. That makes sense. And does it? Well, I guess. Are you able to control? Okay. Are you able to control then the type of structures that you're able to get out of it? And at this point, are there certain structures that you're able to make? Like what kind of structures are?
Yeah, that's a fantastic question. Yeah, so sort of as proof of concept, we started with molecular weight tuning.
Okay.
And so our very first paper, we showed that we could tune molecular weight across, a certain range.
Okay.
So for example, if my nickel catalyst can give molecular weight of like 200,000 grams per mole,
Hmm.
versus the nickel lithium could give up to 700,000 grams per mole, that means my catalyst can access that entire range.
Hmm.
So that means using this system, I can make a polymer of 350,000 molecular weight, or 575,000 molecular weight. So within this range dictated by your two catalysts, we can access anything within that range.
Okay.
And that's unique because no other system can tune that finely.
Right. And what's the fundamental like you mentioned, it was the dynamic equilibrium, I guess, between
Right.
lithium bounding versus, or whatever the metal is. I guess in this case it's lithium, but so lithium bound to nickel versus unbound. But I guess something that is a bit unclear to me then is, well, perhaps is my ignorance kind of with how like, polymer science in general, but it doesn't make. I guess something that doesn't really make sense is the molecular weights. Then, like what exactly is happening then
Yeah.
to control the
No,
weights?
it's a little bit difficult to explain without kind of pictures, actually.
Fair enough.
But so this is a dynamic process, right? So let's say in the absence of switching, let's say your nickel only catalyst, you run your reaction and it gives a molecular weight of 200,000.
Mm-hmm.
And then if you make the nickel lithium complex and you run that reaction, you get a polymer of 700,000 molecular weight.
Okay.
And so the reason they have different molecular weights is just the relative rates are different. So the lithium, because it gives higher molecular weight, it means it's inserting ethylene much faster, right? And so you have more monomer units, and so hence you have a longer polymer. And so those are my two extremes, 200,000 and 700,000. And so to access polymers within that range, let's say 300,000, we can rely on that exchange equilibrium.
Okay.
And the way we control it is by the stoichiometry of the lithium.
Gotcha. Okay. I think that was ultimately my question, was like, is it, what do we, that makes sense though. Go ahead.
Actually,
I'm sorry.
So two factors, the stoichiometry and the solvent conditions.
Okay.
So we've discovered that if you have slightly polar conditions, you add a little bit of ethyl ether, you promote the exchange of that cation. And depending on how much cation you have in there, that rate on and off, right? You'll have different populations of the nickel-only species versus the nickel-lithium species. And so because of that, you can control what species are catalyzing the polymerization.
Right.
And then
that makes sense.
That controls the molecular weight of that polymer.
That makes, that made sense. That was ultimately questions, like how are you able to control the molecular weights? But yeah, controlling the stoichiometry of, well, I guess whatever the counter cation is, that makes a lot of sense. And are you gonna, what's kind of the future of this project then? Like, where do you kind of see it going?
This idea of dynamic switching, because it is very new, we're still kind of exploring the limits and within the application. Now, that's a fantastic question. So the next thing we're moving to we do molecular weight, but now we could do branching tuning. We could tune comonomers, right? So we haven't even touched that yet,
right?
So potentially we could basically control composition of the polymers, structures of the polymers, modality. That's another thing that we could do, is we can change the whether it's monomodal versus bimodal. So what we found is that if under switching conditions, we can make monomodal polymers, because basically the same catalyst is polymerizing catalyzing the polymerization. Under non-switching conditions, specifically using non-polar solvents, we don't get switching. So the lithium is not moving back and forth between the lithium, the nickel complexes. And so in that case, we're getting two different polymers. And so we see that in the bimodal distribution of your polymer product.
Yeah, that's so cool. And I'll say this too: if you're considering going to graduate school and you're interested in polymers, definitely consider Houston. We have such great polymer science here. Honestly, like it's really cool, state of the art stuff here. But that's really cool. Do you have a general sense of what we could maybe touch on this a little bit, but the idea of incorporating a polar monomer, why is it so difficult?
Right.
Yeah, but let's touch on that a little bit, because I think it's an important
so the
detail.
Fundamental problem is that the polar groups, they can bind to the catalyst. So there are multiple reasons why it slows down the catalyst. One of the main ones is that once it inserts into your nickel alkyl bond, you have your polar group. And so when I say polar group, I mean like acrylates or things like that. And they're like carbonyl.
Anything with like oxygen, really, honestly.
Anything with oxygen, right? and it could basically form a back back chelate, right? So it forms this very stable metallocycle, and that's problematic because for polymerization, you need to be able to bind a second monomer, like ethylene, for example, to continue to grow out your polymer chain. And so that's the fundamental problem is, well, how do you keep it from forming that strong chelate? And so one concept that we're exploring is using two metals, right? Because we have these bimetallic systems. Our hypothesis is that when we have a harder Lewis acid, that's why the alkali metals were used.
Oh, okay. I
And
see where this is
because of
going.
the
That's
different
really cool.
preference, maybe it'll bind to the lithium instead of binding to the nickel, right? And it opens up that coordination center.
Yeah, that's an excellent. Yeah, that's a great idea. And then I guess one other question then is, how is the stoichiometry? It's like nickel to lithium. Like, is it 100-to-1, 2-to-1,
Yeah.
4-to-1? Like, has it?
So it depends on whether we're operating under dynamic switching or non-switching conditions. I think we usually try to use up to 2 equivalents to push the equilibrium toward the bimetallic, if that's what we want. If we were trying to exploit the switching, we could use anything between 0 to well, not 0, but anything greater than 0, up to like 2 equivalents, I think.
Gotcha. Okay. And
we don't use a huge excess. We at most use 1.5 to 2 equivalents.
It's just like normal lithium salts then too. Is it just kind of like how do you?
Yeah, great question. We usually use like the barphate anions.
Okay.
So
Classic.
because we need something that's non-coordinating.
Yeah.
Anything that's coordinating will compete as a ligand with our nickel, and so that's why.
And how is important the ligands that you're bound to nickel is? I assume it's homogenous. I assume it's homogenous, or okay.
Yep.
And how important are the ligands to the nickel or the other? Like, what ligands do you use for these systems?
Yeah, so we've looked at several different ligand platforms over the years. We started with the phenoxyimines, and those ligands are great because they're relatively easy to make, and so we like that a lot.
Is that the Grubbs type? Is it right?
Yeah,
is it
exactly? Those are the Grubbs type catalysts. The limitation with those systems is they don't incorporate polar monomers very well. So it doesn't work at all for acrylates, vinyl acetates, vinyl ethers. So it's sort of limited in the scope of monomers that work with that catalyst.
Is it well? Because actually, this is like a kind of a side, but because we were literally just talking about the Grubbs type catalyst for some of the groups ORP. We were talking about how the Grubbs are actually not good for including polar monomers, but I do remember Brad saying it's actually not. I remember him saying, or maybe he was saying that it's actually not really well understood why that is. I don't know. Is it well understood why?
That is correct. As far as I'm aware, that's still unclear.
Alrighty, so just right before we got rudely interrupted by the internet crashing, Jesus, we were talking about why the Grubbs type catalyst can't do polar monomers, and and like we were saying, it's kind of not really well understood exactly why.
Yeah, so the jury is still out on that, and that's something that we ask often. And so, for example, we're currently working with the nickel phosphine phenolate systems, and those do work for polar monomers.
Okay.
And so structurally, they look very similar. Of course, electronically, comparing the difference between an imine versus a phosphine. So, there are probably some interesting differences there. But I think that's something that hasn't really been studied in depth, is why the phenoxyimines don't work.
Yeah, I don't know.
I don't have a good reason. Yeah, that's something that I would love to get into more.
I think that's a whole area of, probably a whole area of research that someone, hopefully someone's working on it right now, honestly. I'm sure there's a question out there.
Right.
Hopefully someone can isolate some structures or try and say some off-cycle catalyst, probably. Yeah, who knows?
Right. Or just maybe do like stoichiometric reactions, right?
Yeah.
Is it doing the insertion at all? Maybe it's just a decomposition of the intermediates or something.
Right. Well, the last thing I wanted to ask you about before we get was before we get going here is the Center for Integrated Catalysis. It's a kind of organization that you're a part of. And well, honestly, is it an organization? I'm not really exactly sure. I don't know. Maybe you could just tell us a little bit about it.
So this is part of the NSF Center for Chemical Innovations, and so NSF
Mm.
has been sponsoring several of these national centers. And so the idea is to work on really ambitious scientific problems by combining different expertise in chemistry. And so the center that I was part of is the Center for Integrated Catalysis. And the idea behind the center was to be able to do multi-step reactions in a single vessel, right? And so, I'm sure you have experience with this. The reason that we often can't do that is because of incompatibility issues,
Mm.
right? If you, let's say you have a 3-step reaction that requires 3 different catalysts, 3 different reagents and solvents and so on, often if you just put it all into a single vessel, you just get a mess, right? So that was a challenge that we wanted to address, is how do we do something like that, right? How do we simplify synthesis so that we could just put all our reagents together and then get out our final product? And so the concept that we were trying to explore is to use spatial and temporal control,
Mm.
Meaning that spatially, maybe we could separate the catalysts if they're incompatible with each other. We could use different strategies to confine the catalyst, let's say like in an emulsion, for example. And we also wanted to use temporal control, meaning that we want to be able to switch the catalyst on and off at different times.
Mm.
So it was definitely a very ambitious goal, being able to demonstrate both the spatial and temporal control to achieve multi-step reactions
Right.
in a single vessel.
And how did you kind of get involved with it then? Was it kind of someone approach you, or is it something that you?
Yeah, so Paula Decanescu, who is the lead in our center, she's at UCLA. I think originally she was interested in kind of bringing together folks who are working on switchable catalysis.
Mm-hmm.
So Paula's lab at UCLA works on redox switching, and so our lab has been working on cation switching. So she was trying to bring together people with that expertise. We also then brought in a few other sort of materials experts as well. So we got Dunwei Wang from Boston College, who studies heterogeneous catalysts. We have Chong Liu at UCLA, who does also more heterogeneous catalysis and also flow chemistry.
Mm-hmm.
So we kind of brought in the expertise, and I think the idea of the integrated catalysis kind of came about during our early meetings.
Yeah.
We were still trying to figure out our identity and what exactly we were trying to tackle. And so that's kind of the origin story.
Yeah. Definitely. I like when I guess a bit of a somber note, but yeah, when I had on Professor Jeff Byers, 2 years ago now on the podcast, he tragically passed away back in August. I still can't believe he's gone. We really lost a great person. Yeah, I was talking to him about, because he does a lot of great iron work, like iron cross coupling, but also polymerization. So it's great to see that this even exists. And so, I'd love to, if you're interested for this type of collaboration, and catalysis is definitely something that to keep an eye on. And so I know you guys do really good programming too. So be on the lookout for that. But I think with that, we'll conclude here. Professor Doe, I want to thank you so much for coming onto the podcast today. We always pass each other, but it was finally get to sit down and actually do this. So just want to thank you for your time, and it's great chatting with you.
Yeah, you too. Thanks a lot, Aiden.
All right, everyone. Well, thank you for joining into another episode, and we'll see you on the next podcast.